All right, this is section 13.5. This is lines and planes in space. We're going to split this section up into two parts. So part one is going to be lines. We're going to look at an equation of a line. So just like we normally think of a line, this is literally a line, but it's going to be in three space. And we're going to look at the two different ways that we can look at the equations as either vector equations or parametric equations. So to start, we're going to look at the equation of a line in R2. So I don't know if I've talked about this notation just yet. That scripty R means that we're looking at the real numbers, and then that little exponent of 2 means that we're looking at two dimensions. So we're looking at the xy plane. So lines are usually defined by a point and a direction. Now, we don't normally call it the direction, we usually call it the slope. But that's what the slope is. It's telling us the direction that the line is going. So think about what we've been using to talk about direction. We've been talking about vectors. So keep that in mind. But normally, we start with some particular point on our line. So in this case, we'll call it x sub 0 and y sub 0. So that's going to be some point we know that are actual values. And then we're given that slope, and that's telling us our rise over run, and that's telling us how to get to other points on our line. So that slope is our direction. It's telling us to go, that much in the x direction and then that much in the y direction. And that gets us to some other point on our line, and it isn't necessarily a specific point. So I'm going to call it just xy because it can be any point. Those are actually going to end up being our variables. And that slope, which we call m, is y minus y sub 0, x minus x sub 0. Now, normally we have those as both values if we don't know what the slope is. But if we know the slope, say the slope is 2, and then we know a specific point on our line, we can solve this equation, or I guess just rewrite it is a better way to say it. And we can multiply both sides by that x minus x sub 0. And if we know that specific point, say it's something like 4, 7, and our slope is 2, we can plug that specific point in, plug our slope in, and we can get our equation of our line. And that is the equation of the line. It's not written how we normally liked it written. Normally we like to write it in that slope-intercept form. So there it is in slope-intercept form. But if we've got that specific point on our line and our direction, we can get the equation of our line. So remember, that's our direction. Okay. So the equation of a line in R3, we're going to need the same things that we need in R2. So R3 is just 3 dimensions. So we still need a specific point on our line. So these are going to be actual values here. So this is going to be a point. And then we're also going to need some sort of variable point, and this is going to be any other point on our line, and this is going to stay variables. So this is like that second point we had on our line in 2 space. It's going to stay as x, y, and z. Then we also need our direction that we want our line to go in. So what we're going to do is define a vector, some vector v, and again, this is a position vector, but it's going to be parallel to our line. So what it's saying is that our line points in the same direction as V. It's telling us what way to go. Sorry that my handwriting is getting a little bad there. But it's telling us where we're going to go. So let's look at this in terms of a picture and with our actual equations here. So here's our our coordinate system here. So if we've got some point up here, so x sub 0, y sub 0, z sub 0. This is some specific point that is sitting out in space that we know we want on our line. So we can then also think about, okay, we've got our vector v, which is giving us our direction, and its coordinates end up at A, B, and C. So we want our line to go in that direction. So we want our line to be parallel to that vector v. And to get other points on our line, what we're going to do is take this vector and maybe multiply it by some scalar, and that's going to end up at other points on our line. So this is going to give us a way to find all the other points on our line. And that's the whole point of having an equation. If we go back to this equation right here, that gives us other points on our line. We know one of our points is 4, 7. But if I want other points on that line, I can plug in some values for x, and that will give me other y values, and it will give me other points on my line. That's the whole point of coming up with an equation, is that we want a way to get all of those other points that are on our line. So how we're going to look at that is we're going to look at making that point we have a position vector. Right? We can do that really easily. Its position is x sub 0, y sub 0, z sub 0. So we can go from the origin to that point and make a vector out of that. And then we want to go in the same direction as vector v, but that t, that's right there. So t is going to be a variable scalar that's going to make that vector v different lengths, and it's going to give us multiple points on our line. So if we pick t to be different scalars, so we could pick it to be 1/2, we could pick it to be -2, we could pick it to be 10. If we add that vector v times that scalar to our orange vector here, that's going to give us other points on that line. So this vector equation that we've got here, that x, y, and z are other points on our lines, because again, we could also I'll write this in a color that's not super obnoxious. This is our vector x. Ooh, that is super obnoxious. It's hard to read that. Let me change it to a color we can actually read here. That yellow vector ends up at x, y, z at some other point on our line. So that vector, we can get to it by adding that initial point vector plus our scalar times our direction. So another way to write this equations of these lines is with parametric equations, where we basically split these up into the components. So x is equal to that initial x value, and then that position vector, the x component, times that scalar, and that's going to give us our new x point. Same for y, it's that y sub 0 plus the y component of that direction vector times t. Same for z, we get z sub 0 plus that c, which is the z position in that direction vector, times that scalar. So let's take a look at how this looks with numbers, and we can kind of talk about, how we get other points on the line. So our example is find the equation of a line through the point 4, 1, 6 and parallel to the vector 7, 3, 0. So this point right here, that's our p sub 0. That's that initial point, sort of that starting point that we're going to use to get to other points on our line. And then this is our direction vector telling us what way to go from that initial point. So the vector equation of our line, we get a vector, our variable vector, x, y, z, it's equal to our point turned into a position vector plus that scalar variable times our position vector. And that's it. That is the equation of that line. That's the vector equation. The parametric equations are going to be splitting this up into the x component. So we get to the x value by doing 4 plus whatever our scalar t is times 7. We get to y from 1 plus 3 times whatever we make our scalar variable, and z is 6 plus 0 times t. Ooh, 0 times t, that means it's just 6. So what this is saying is that this line, that t or the z variable, is always 6 on this line. So this is actually going to be parallel to the xy plane and always going through z equals 6. So if we wanted another point on this line, I mean, because that's it, we found them. So don't think we need to do anything else. Like if we were just asked these two things are the answer, depending on if you were asked for the vector equation or the parametric equations. What I want to talk about just here for a second is how we actually use these equations. So another point on this line, we can find that by picking any value for t. Pick any value for t. The domain is all real numbers because it's a line, so you can pick anything you want, and that will give you another point on the line. So if we pick something like -2 and plug in that for t in all of our little equations here, that is going to give us another point on this line. Well, z is always going to be equal to 6. But what this is going to give us is the point -10, -5, 6. That's another point on this line that we've made. We could pick t being a different thing, and that would give us another point on the line. So we could keep doing this for as much as we, as long as we want to get other points on the line, just like we can with any linear equation. Okay, let's take a look at another example. Because a lot of times when we're finding equations of lines, when we're talking about it in 2 dimensions, we're given this information. Oops, sorry about that, find the equation of the line through 2 points. So when we have this, the first thing we have to do when we're in 2 dimensions is find the slope. That's the same thing we need to do here. We've got to figure out what is our direction. So we're figuring out what's the direction. Maybe we'll call that P and maybe we'll call that Q. We got to figure out the direction from P to Q. So that's really just finding the vector that starts at P and goes to Q. You could do it the other way too. It doesn't really matter. That's kind of the nice thing about this. It's the same as when we're finding slope. When you have, the point x1, y1, and x2, y2, you can label those 2 points whichever way you want. It really doesn't matter, because your slope is going to be the same slope no matter what. So your direction, whether you're going forward or backwards, it's really not going to matter because it's the same direction. So here's our direction vector. So we can call that v if we want. That's helpful. Now, our point on our line that we're going to use to get our vector and parametric equations, it doesn't matter if we use p or q. It really doesn't. It's going to look a little different if we use q versus p. Because that point that we pick to make our equation of our line, that's sort of our starting point, and then we go in the direction from that starting point. So that starting point is going to make things look different, but whether we use P as the starting point or Q, we get to the same points on our line. So our line here with P as the starting point, it's going to look like this. We're going to use 5, 7, 9 as that starting point and then do some sort of scalar multiple of our direction vector. And the parametric equations are going to be 5 plus 7t, y is going to be 9 minus 3t, and z is going to be 7 plus 3t. If we instead, we said, okay, let's use q as the starting point. It doesn't really matter what you use as the starting point. Our vector equations and our parametric equations are going to just look slightly different only because that starting point's different. But the direction that we go, that's going to remain the same. And it's really just a matter of sort of thinking back to a line in 2D here. Let me finish writing this out here. 10 plus 3t. Okay, so notice like these parts of it are the same. It's just that starting point that's different. If we go back to our line in 2D, so that point that we had as our starting point, we can use that and then use our slope to get to other points on the line, right? And then we can get to another point, we can go back and down and get to that. But we could have used this point as our starting point, and then we could have gone down and back and got to that point. So whatever you pick for your starting point, if you know what the slope is, you can get to other points on your line. So that's why back over here, it doesn't matter whether we use Q or P as our starting point. As long as we've got our direction right, our slope right, we're going to get to the other points in our line. All right, one more thing with lines. So lines in R3, if we're looking at 2 different lines, they can either be parallel, they can intersect, or they can be skew. If they're parallel, that means that their direction vectors are multiples. right? It's basically saying it goes in the same direction. So they may not be, near each other, but they're going in the same direction. They have the same slope. If they're intersecting, they're going to intersect at one point. I mean, we can also have that the two lines are the same. That's not that interesting, but we can have that. Um, but then skew is that they're not intersecting, but they're not parallel. And this should make sense. I mean, you can have two trajectories in 3 dimensions and they just will never touch each other. You could have one sort of up here like this and one down here like this, but we got to think about this in 3 dimensions. So that might be a little easier to talk about in class when I can actually like kind of show you your hands. But think about your arms. You can set those up in a way that one's got a slope that's different than the other, and they would never actually intersect each other in 3 space. So we can ask a question like, oh, I don't know how that slide still ended up in there. That one wasn't supposed to be there. I'll make sure I take that out in the notes. Are these lines parallel, intersecting, or skew? So parallel is pretty easy to take a look at. You want to look at the direction vectors for each of these. So our direction vector for our first line, that comes from those coefficients of t, because that's telling you your direction. So our direction vector here is 5, 4, and 1. And over here, we labeled our scalar multiple a different variable. We labeled it S. That's just to keep our two lines separate. So our direction for our second line is 3, -1, and 2. So those directions are not multiples of each other. They'd have to be scalar multiples. So we're not parallel. All right, so then I look for intersecting. Okay, that's this. So you always start, say, number one, are they parallel? Because that's the easiest thing to look for. 2, you should look for, are they intersecting? So we're looking for, are these going to intersect at a point? Okay, so we want to see if there's ever a time where the two x values are equal, the two y values are equal on our lines, and the two z values are equal. So we can set each of these little 3 equations equal to each other. Now there's a lot of ways to solve these. What I look for is I look for either an s or a t that has a coefficient of 1. And we do have a winner right down here in our third set of equations here, or not set of equations, in our third equation. This one right here, I can add 2 to both sides and say that t, for this to be true, for those two lines to be equal, for those two z values to be equal, t would need to be -1 plus 2 times s. All right, well, we can take this and plug this into one of our other two. It doesn't matter. You can plug it into either. So it's your choice. Let's see. I think I plugged it into the first one. So it doesn't matter. Oops, and then I didn't plug it in. Didn't plug it in for t. That's what we need to do. We need to replace that t with the 1 plus 2s and 10, and so then we get equals to 10 plus 3s. So this we can solve. This is an equation in one variable. So let's see here. We've got -4 plus 10s is equal to 10 plus 3s. So we need to add 4 to both sides and subtract 3s from both sides, so that we get 7s is equal to 14. So we get s is equal to true, or s is equal to 2. So what this is telling us is that if this is true, if these points, if we've got some point x, y, z that's the same on both of our lines, it's true for that second line when s is 2. Well, I want to figure out what t would need to be. So I go and I can take and plug that back into here. T would need to be -1 plus 2 times 2. Okay, t would need to be 3. So what we need to do at this point is to see if they actually do intersect. We need to see, okay, what is x? What is x when t is equal to 3? What is y when t is equal to 3? What is z when t is equal to 3? So what is this point? This is 16, that is 15, and that is 1. So this is our line 1. Then let's see what happens when we plug these into line 2. What happens when S is 2? We hopefully will get this exact same point that we got when T was 3. So we're plugging in 2 for S in all of our points here. So wow, lo and behold, that's 16, that's 15, and that's 1. So these two lines intersect at the point 16, 15, 1.